Welcome back. All right, so we're going to jump right into some right-angle trigonometry. So here's what we're looking at so far in this video. We're going to introduce or remind of some basic trig functions, sine, cosine, tangent, all that kind of stuff. Again, I expect some of you have seen these, maybe some of you haven't. No big deal. They're not terribly difficult to wrap your mind around. Then we're going to remind ourselves about the Pythagorean theorem. We're going to look at two special right-angle triangles. These ones you will need to memorize. Oops, let me get that straight. There we go. These special triangles are going to be super important, super helpful to know for this class, but also for Calc 1 and Calc 2 and all that kind of stuff. It's going to just make your lives so much easier if you just learn them now. So they're only two. They're very easy to memorize. I'll try and kind of explain how those go. Then we'll talk about some basic trigonometric identities, and we'll briefly talk about some applications at the very end. So that's what we're looking at today. So here's your introduction to some trig functions. If you've seen these, great. If not, here they are. Here's the name of these functions. Here's how we'll abbreviate them, what they'll look like, and then here's how we'll write them as functions. So we've got our sine function, S-I-N-E for sine. We'll abbreviate it S-I-N. So when you see this, we'll read that as sine. Similarly, our cosine function, we'll read this as cosine, we'll read this as tangent, we'll read this as cosecant, we'll read this as secant, we'll read this as cotangent. Sometimes these two will flip the order that they're in, and we'll have sine, cosine, tangent, secant, cosecant, cotangent. There's no real rhyme or reason to whatever order people write them in, but typically those are the main ways that you'll learn them. I don't know. Anyways, this is how they look. F of theta is sine theta. Theta is our input angle, and so we include it as our input in parentheses. Sometimes, though, most times, we'll write it without the parentheses there. We're used to having things like f of x is, I don't know, like square root of x squared plus 4, right? Where x is the input. It's the exact same as like parentheses x squared plus 4. But most times we don't really need those parentheses on here. So with this function name, we'll do the same kind of thing. I expect that you saw this with like a natural log function. Maybe you wrote it as natural log of x or just ln x, same thing. Don't really care how you write it, but you'll see it in this way mostly. So tangent is TAN, cosecant is CSC, secant is SEC, and cotangent is COT. These are our 6 trigonometric functions. Really, there's only 3 that you have to know, and all the other ones are co-versions of it. So there's sine, and then there's cosine. There's tangent, and then there's cotangent. And there's secant, and there's cosecant. Most times, we group them in a bunch of different ways. Sine, cosine, and tangent get grouped together sometimes, and then secant, cosecant, and cotangent will get grouped together. Sometimes sine, tangent, and secant will get grouped together, and then all the co-versions, cosine, cosecant, cotangent, will get grouped together. And we'll talk about why later. Honestly, some of those groupings don't come until calculus and things like that, so you'll find that they get grouped naturally in different kinds of ways. Anyways, those are our 6 trigonometric functions. What the heck are they? Because right now we just have little names for them. Well, they're going to be based on right-angled triangles. So before you even care about any of this stuff, let me just draw a right-angled triangle. This is going to be like the backbone of what basic trigonometry is built on. So there's your right angle, and I'm going to pick one of these angles here as theta. Now, in our last video, we talked about how we're normally going to draw angles in standard position and blah, blah, blah on a set of coordinate, on the coordinate plane. We'll come back to that. For now, let's just say this is our triangle. So we have 3 sides of our triangle. Obviously, I've got a nice text thing, so I don't have to write all this. Obviously, this side here is our hypotenuse. Oops, if I can spell that correctly. Our hypotenuse is the longest edge of our right triangle. The opposite side is whatever one is opposite of our angle. And the adjacent side is the one that's running alongside of our angle. So there's one way that we could draw this. Another way that we could draw this is same right triangle approximately. Right angle here. But now I'm going to go ahead and put theta over in this corner. Our hypotenuse is still right here. But now you'll notice this side is the opposite side, and this side is the adjacent side. So the orientation of these is really going to be based on where we draw our angle. So what I want us to focus on is sine is the opposite side over the hypotenuse. Cosine is the adjacent side over the hypotenuse. Tangent is the opposite side over the adjacent. Cosecant is, I'll put this in red, the hypotenuse over the opposite side. Secant is the hypotenuse over the adjacent side. And cotangent is the adjacent leg over the opposite side. And notice again, these are all lengths of these sides. So all these trig functions, their inputs are angles, and their outputs are ratios of these side lengths based on the way that our triangle is built. So you can see pretty easily right off the bat why we kind of group these into our functions and our cofunctions. Sine is the opposite over the hypotenuse, and cosecant is the kind of opposite of that. It's the hypotenuse over the opposite. Cosine is the length of the adjacent side over the length of the hypotenuse, and secant is the opposite one. Oh, I think I said group this into cos. Yeah, I mean, sorry, I didn't mean cos, because this isn't sine, secant, tangent. Let me start that over. We have a natural grouping. Sine, cosine, tangent get grouped together. Cosecant, secant, cotangent get grouped together. And it's based on the ordering of these ratios, right? The hypotenuse is on the bottom for these two. The hypotenuse is on the top for these two. In this one, we have opposite over adjacent. Here we have adjacent over opposite. There's a nice little memorization tactic that we can use for this that I expect that you've seen if you've done some high school trig. SOHCAHTOA. SOHCAHTOA just stands for these ratio orders. So sine, that's our S, is opposite side over the hypotenuse. Cosine, that's our C, is the adjacent side over the hypotenuse. And tangent, that's T, is the opposite side over the adjacent side. So all these letters just tell us what order we have. I expect that some of you have seen that, maybe most of you, if you've done some high school trig. But that's what we've got here. So let's just take a look at an example real quick. The Pythagorean theorem, just as a little recap, says that for a right angle triangle, if A, B, and C are the side lengths and C is the hypotenuse, A squared plus B squared equals C squared. This is the main thing for the Pythagorean theorem. So let's go ahead and just draw up a triangle. I don't know, I'll just make one up. Let's say here's our right triangle. And I need some side lengths. Let's say this side length is 2. And let's say this side length is 5. And let's put our angle theta right here. And then I'm going to do another example in blue. Actually, no, let's do the green one first, and then I'll do blue after, and I'll let you do that. So if we want to find sine of theta, cosine of theta, tangent of theta, cosecant of theta, secant theta, and cotangent of theta, we need all three legs, because remember, we got to have the opposite, adjacent, and hypotenuse on all these things. So let's figure out the hypotenuse using the Pythagorean theorem. I'm going to let you pause the video and just do that real quick, and then I'll come back and have that done. So I'm not going to waste too much time on that. Go. All right, hopefully you got square root 29. So when we want to find sine of theta, we're going to say it's the opposite side. That'll be, maybe I'll grab my highlighter. Oops, there we go. So it's our opposite side, 5 over the hypotenuse, root 29. So we're going to say this is, there we go, 5 over square root 29. Let me write that a little bit cleaner and a little bit smaller. Perfect. Cosine, then, is going to be the adjacent over our hypotenuse. So that's going to be 2 over square root 29. And then tangent is the opposite side, 5, over the adjacent side, 2. And then we might remember that the cosecant is just kind of the flipped version of sine. So this is going to be the hypotenuse over the opposite. So this is going to be root 29 over 5. Secant is the flipped version of cosine, so that's root 29 over 2. And cotangent is the flipped version of tangent. That's 2/5. Sometimes you'll see people rationalize these denominators where you multiply the square root out and all that kind of stuff. I don't really care about that, to be honest. If you want to know why, we can talk about that later. But anyways, that's what we've got. I'm going to drop another example in blue, and I'll let you guys do that by yourselves, and I'll just put in some answers for you. So let's do this. Let's say we've got a nice right angle triangle here. And let's say that our angle theta, I'm going to switch it up, and I'm going to put it up here. And what I'm going to do, I'm going to give you the hypotenuse instead, and I'm going to give you one of the side lengths. I'll say this one is, I don't know, we'll say this one is 6. All right, I'll let you go from there. So pause the video, fill in that third side length, and see if you can fill in all 6 of the outputs of these trig functions. Go. All right, so hopefully this is what you've got. We've got 81, or if we do the Pythagorean theorem, let me write this out. We've got 6 squared plus b squared equals 9 squared, so 36 plus b squared is 81. So b squared is 81 minus 36. That should be 45. And so we've got that b is the square root of 45 in this case. Or we can reduce that, or not reduce it, simplify it. I forget what they call it. Rewrite this as just 3 root 5. And so then when we have sine, we're looking at our opposite side over the hypotenuse. So this is 3 root 5 over 9, which we can reduce. Root 5 over 3. And then from there on out, we get everything. Cosine is 6 over 9. Tangent theta is 3 root 5 over 6, or just root 5 over 2. And then cosecant theta, secant theta, and cotangent theta just kind of fall out from there. Hopefully, that goes pretty well for you. We can take a look at some more examples if you want. I did put in some more spot for these. Maybe I'll just draw up some things and fill them in, and you can kind of go from there. I'll just do one more. So let's do, I don't know, something like this. And I want to do a nice, I don't know, pretty easy one for now. Oops, I forgot to take my straight line tool off. There we go. 1, 3, that should be good enough. And let's put theta here. So we can use the Pythagorean theorem and say that this is going to be the sum of the squares of these things, and we're going to square root it. So hopefully you get root 10. 9 plus 1 is 10, so we'll take a square root of that. And so you can kind of fill things out from here. So again, pause it, go from there, see what you can do. All right, so this is what we've got. Sine is 1 over root 10. If you want to rationalize the denominator, if you multiply the square root of 10 on the top and the bottom, you get root 10 over 10. Maybe people have seen that, maybe not. I don't really care what you do here. Cosine is 3 over root 10. You could do the same thing and get 3 root 10 over 10. Tangent is 1/3. Cosecant theta is root 10 over 1. It's just root 10. Secant theta is root 10 over 3. Cotangent theta is 3 over 1, or just 3. Cool. So now we've got 2 special triangles that we want to know. There's 2 very special right triangles that are going to be really helpful to just have things kind of memorized on here. So these are the triangles. I'm going to write in some angles on here. I should have probably drawn in that these are the right angles. And this one is, you may have heard this as like the 30, 60, 90 triangle. This angle here is 30 degrees. Maybe I'll just do this. That's better. 30 and 60. And this one is the isosceles triangle. Well, we'll get to that one in a second. So let me draw the little degree symbols on here. There we go. 30 degrees, 60 degrees. In radians, then, we could convert that. And I'll let you do that as much as you'd like. But that's going to be pi over 6. That's going to be pi over 3. Our other triangle is an isosceles right triangle. Since it's isosceles, we know that these 2 angles have to be the same. And since we know all the angles add up to 180 degrees, these have to be 45 degrees. So these 2 triangles are very special. Oops. My degree symbol got all janky. There we go. In radians, then, this is going to be a quarter of 180 degrees. So this is pi over 4, and this is pi over 4. And what we can do is we can just label all of these things really nicely. The isosceles one is probably the easiest one to start with. Since it's isosceles, we know these side lengths are the same. So let's just pick a value for them. Let's say the side lengths are 1. That means that the hypotenuse is going to be the square root of the sum of the squares. 1 plus 1 is 2. So this is a 1, 1, root 2 triangle. That one I do not think you need to memorize. Just know that we need to know the isosceles triangle. Since it's isosceles, these two angles are the same, and these two sides are the same. And once you know that, you're good. You can build everything from there. The 30, 60, 90 triangle is a little bit trickier. The main thing that I remember is that the small side is half the length of the hypotenuse. Or you could say the hypotenuse is double the length of the small side. Cool. Then for this one, we're going to need this to be a square root, and it's going to be a difference of the hypotenuse squared minus this leg squared. So this is going to be the difference of 4 minus 1. So this is root 3. So I remember that the small side is half the length of the biggest side, and then you can get everything from there. So let's just figure out sine theta, cosine theta, all that kind of stuff. And let's pick theta here to be pi over 6 for this one. So for pi over 6, that's this angle here. So well, maybe I'll draw in my theta here. So sine then is going to be, that's going to be the opposite over the hypotenuse. So that's a half. Cosine then is the adjacent leg over the hypotenuse. So that's root 3 over 2. And then tangent is opposite over adjacent. So that's 1 over root 3. Cool. If we wanted to do, if we wanted to do theta being pi over 3 or 60 degrees, if we put theta there, then we can get sine and cosine really nicely. We'll say sine is going to be the opposite over this, so this is going to be root 3 over 2. Cosine is going to be the adjacent leg, 1 over 2. And tangent is going to be the opposite over the adjacent, so that's going to be root 3. And over on this one, doesn't really matter which one we pick. Theta is going to be pi over 4. So sine is going to be 1 over root 2. Cosine is also 1 over root 2, which is weird until we think, oh, of course, these two side lengths are the same. It's an isosceles triangle, so the opposite and the adjacent sides are the same. And that means that tangent is going to be 1. So these values are going to be really important for us to know, but I don't think you have to memorize any of the values themselves. I think just knowing what these triangles look like is pretty good, because then you can get sine and cosine and tangent really easily from there. So nothing too big, but get to know these triangles. Hopefully, that'll go pretty well for you, and that should be nice. I want to talk about some identities with trig functions. These ones we've pretty much seen already, that sine and cosecant are reciprocals of each other. Cosine and secant are reciprocals of each other. Tangent and cotangent are reciprocals of each other. So they're linked across here by just saying we can flip them upside down and get the other one. We know that sine is the opposite over the hypotenuse, and so cosecant is the hypotenuse over the opposite. It's the reciprocal of sine. This one is a little bit interesting, though. Tangent is really sine over cosine, and we can see that really nicely because sine is the opposite over the hypotenuse, and cosine is the adjacent over the hypotenuse. That's really opposite over hypotenuse times the hypotenuse over the adjacent, divide fractions, so we flip and multiply. And so you can see the hypotenuse cancels out, and this is really just opposite over adjacent. That's tangent. Cotangent is the reciprocal of tangent, and so we just flip them around here. So not too bad. These reciprocal identities are really important. This quotient identity is really important. We can go back and say, hey, look, if we look at tangent, that's really a half divided by root 3 over 2, or times 2 over root 3. The 2's cancel out, and we get 1 over root 3. Easy enough. Tangent here is really 1 over root 2 divided by 1 over root 2. Those are the same values, so it's just 1. Easy enough. So we really only ever need to be able to find sine and cosine because you can get tangent from there. And once you have sine, cosine, and tangent, you can get cosecant, secant, and cotangent super easily. So sine and cosine are really the only ones that you need to be able to find. So that's what I'm saying here. We can use identities to find the rest. So maybe what I'll do is I will give you some values for sine and cosine, and you can go ahead and fill in the rest of these things just to see what we've got. So let's say, for instance, that we know that sine theta is 1 over root 5. And we also know that cosine theta is 2 over root 5. We should be able to find tangent theta, cosecant theta, secant theta, and cotangent theta really easily. Cosecant theta and secant theta, we can just grab right away. We know that they're reciprocals of these ones. So if we know that this is 1 over root 5, bang. This one's root 5 over 1 or just root 5. And this one is root 5 over 2. So now we just need to find tangent theta, and then we can flip that upside down and get cotangent. Tangent theta is going to be sine theta over cosine theta, which is 1 over root 5 over 2 over root 5. That's 1 over root 5 times root 5 over 2 if we flip and multiply. And that's really just a half. So tangent theta is half. And then if we want to get cotangent theta, that's clearly just going to be 2. So not too hard. Once you have sine and cosine, those values, you can use the reciprocal identities to grab cosecant. Oops, sorry. There we go. These ones. To grab cosecant theta and secant theta. And then you could use this one to get tangent theta. Now, what you also might notice is that we really could get a whole bunch of different things out of this. We could go ahead and just give you cosecant theta and maybe tangent theta. And if you have cosecant theta, you can get sine theta. And then if you've got tangent theta and sine theta, you could figure out what cosine theta is and go from there. So really, we don't even just need sine and cosine. We need two values that aren't reciprocals of each other, and then we can be able to find the rest there. So that works out pretty nicely. And we'll play with these kinds of problems more, but hopefully it works out using these kinds of identities. The next thing that we want to talk about is the Pythagorean theorem. So here's a quick reminder of what the Pythagorean theorem actually even says. The Pythagorean theorem says, for a right angle triangle, if you've got some side lengths, A, B, and C is the length of the hypotenuse, then bang, A squared plus B squared equals C squared. What you might also notice then is that we can go ahead and convert some of this a little bit. So maybe if we have A squared plus B squared equals C squared, we could divide everything by C squared. Just for fun. Now we've got A squared over C squared plus B squared over C squared equals C squared over C squared, but that's 1. A squared over C squared is really A over C squared. B squared over C squared is really B over C squared, and that's 1. Let me fix this A over here because that looks pretty bad. There we go. And what you might notice is that if we put our angle here, what is A over C? Well, that's our opposite side over our hypotenuse. This is really sine theta. Oof. There we go. This is really sine theta squared. And B over C is the adjacent leg over the hypotenuse, so this is really cos theta squared. So we get this identity. Normally what we'll do is we'll write it this way. I'll put it in black. Sine squared theta plus cosine squared theta equals 1. We put the exponents on the functions just to clean that up a little bit. That's a pretty typical thing that we do with trig functions. Notice that if you put your angle over in this side, then A over C is actually cosine squared now, or cosine, so this is cosine squared. B over C is really sine, so this is sine squared. So you'd have cosine squared plus sine squared, but that's okay because addition is commutative. It doesn't matter what order we write it in. So we could put the angle in either corner here and get the same Pythagorean identity, we call this. It's because it's really just the Pythagorean theorem. So this identity is super important for us. Again, this might be one that you've seen. This might be one that you recognize. From this, you can get other versions of the Pythagorean identity. So here's two more that we can get. And we can just use some nice quotient identities here. For instance, we could go ahead and just divide everything by cosine squared theta. And suddenly, we have sine theta over cosine theta squared plus 1 equals 1 over cosine theta squared. While sine theta over cosine theta is really tangent. So there's our tangent squared theta plus 1. And 1 over cosine, we said by the reciprocal identity, that's secant. So we get tangent squared theta plus 1 equals secant squared theta. And you can do the exact same thing here where you divide everything. Let me just grab all this in one shot. There we go. Where you can divide everything by the opposite trig function. So instead of dividing by cosine squared, why don't we divide by sine squared? And then suddenly we get 1 plus cosine theta over sine theta squared equals 1 over sine theta squared. This is 1 plus cotangent squared theta equals cosecant squared theta. I'll be honest, I never memorized these. I know which functions go together. I know that tangent and secant go together, and I know that cotangent and cosecant go together with the Pythagorean identities. But I rarely have this right on the tip of my tongue committed to memory. I know the sine squared theta plus cosine squared theta equals 1. That one I feel like most students pick up pretty easily. But from there, I'll just think in my head about what would happen if I divided by sine squared theta. What would happen if I divided by cosine squared theta instead? If I want to get the Pythagorean identity with a tangent squared theta here, I know that tangent is sine over cosine, so I'll just imagine dividing everything by cosines. This one here becomes tangent. That one here becomes 1. And this one here becomes 1 over cosine theta. That's our secant one. So things work out pretty easily if you just remember the sine squared plus cosine squared equals 1 version of this. You can get the other Pythagorean identities. Cofunction identities. These are kind of neat. Cofunctions are just the neat little idea that if we have some sort of a right angle triangle here, and we put theta in this corner, then sine of this corner is going to be cosine of this one. It's easy enough to get this measurement. We know that all of these angles have to add up to 180. Since this one here is already 90, that means our two other angles have to add up to 90. So if this one's theta, the other one's just 90 degrees minus theta. So if we have one of the angles here, you can just subtract that from 90 to get the other angle. And then what you'll notice is that the opposite side for my green angle theta is the exact same thing as the adjacent side. Oops, that's not how you spell adjacent. For my blue angle, 90 degrees minus theta. The hypotenuse is the same thing no matter what. I probably should have used the typing thing on here. Oh well. There's my y. So that works out really nicely. Similarly, the adjacent leg in green is the same as the opposite leg in blue. And so then we get that sine and cosine matchup for these things here that we call cofunctions. Tangent and cotangent match up for these other angles, so we call them cofunctions. And secant and cosecant match up. So the co version of this comes from the fact that we're really looking at the complementary angle here. Remember, complementary means that it adds up to 90. So if we look at the complementary angle, that gives us the opposite angle. I shouldn't say opposite because that makes you think of the opposite side length. Gives us the other angle in a right angle triangle, and we can get our other function values from there. So if you wanted, you could go ahead and say things like sine of 70 degrees is the same thing as cosine of 20 degrees. 70 degrees and 20 degrees are complementary angles. You could say that tangent of pi over 3 is going to be the same thing as cotangent of the complementary angle. That's going to be pi over 2. Maybe I'll write it. Pi over 2 minus pi over 3. That is cotangent of... that's 3 pi over 6 minus 2 pi over 6, so that's pi over 6. So tangent of pi over 3 is the same as cotangent of pi over 6. So you can do this with radian measures, degree measures, it doesn't really matter. Drawing the triangle, it makes it pretty easy to see that. Once you grab the other angle, you can grab those other side lengths. Last thing, quick little application. So let's say we've got a road that's inclined at an angle of pi over 20. After driving 6,000 feet, what's the driver's increase in altitude? All right, so let's draw this thing. This is a road that's inclined, so I'm going to draw the road. There it is. We want to find the increase in altitude, so that's the change in height here. So we want to find that. And you'll notice if we connect those things, hey, look at that. That looks like it's probably a right angle triangle. So this is our road. And we want to figure out what this change in altitude is here. Oops, there we go. We have an angle given to us. The angle is this one right here. So our theta equals pi over 20. And we know that the length of the road, that's the distance that they travel, that is 6,000 feet. Cool. So if we want to find the change in altitude, we're looking at the opposite side of this. And so we want to know what the opposite side is of this angle. We have a hypotenuse. Hopefully that makes us think of sine. We know that sine theta is going to be, I'm going to make this, maybe I'll make it x. The change in altitude, x over 6,000. Theta is pi over 20, so we can say sine of pi over 20 equals x over 6,000. So if we want to solve this for x, x is 6,000 times sine of pi over 20. Whatever that is, grab your calculator and we'll see if we can figure out what this thing is. So sine of pi over 20, just this portion right here, is an ugly decimal. I'll just kind of round it off. It's approximately 0.15, oops. There we go, 6 ... I'll put the little approximate sign here. If you didn't get that, there's a problem. The problem is that you're likely in degree mode because pi over 20 is really just like 3.14-ish divided by 20. That's just some number. And if you measure that in degrees, that's just some small angle. And so what your calculator is doing is trying to find sine of an actually smaller angle because it's thinking that this is pi over 20 degrees. Well, that's not what we want. So you can do a couple of different things. You could convert this to degrees if you want. You could say pi over 20 is really 1 over 20 times 180. That's 9 degrees. So you could say, well, this is 6,000 times sine of 9 degrees. And then you should get your 0.156. Or you can go into the mode on your calculator, and you should be able to switch it to radian mode. Depending on the calculator that you have, it's going to be in different spots, so try and make sure that you can find out how to switch between radians and degrees. Don't go anywhere until you get that sine of pi over 20 is 0.156. Now, that's before I multiplied the 6,000 on there. I don't know what that is if I multiply 6,000. Let me just check real quick. It looks like it's 938. Oops, let me put this in green again. So our end answer should be 938.6-ish. So our change in altitude, let me write this here. Our change in altitude is approximately, oops, there we go, 938.6 feet. You can do it using radians. You can do it using degrees. If there's nothing written here, no units written here, we'll assume that this is in radians. If there's a degree symbol, then it's in degrees. So the only time it's going to be in degrees is if you see that degree symbol written on there. If you don't see that, it's in radians. Make sure your calculator is in radian mode. Cool. That's all I've got. Hopefully that works out pretty well. Give me a shout in the discussion boards if you have any questions on that.